let's talk about open channel flow. And we talked about, we mentioned, we've seen this diagram before, we talk about viscous flow, and we said that there was external. We just talked about that. That's chapter 11. All right, so chapter 11 and chapter 8 show up on exam 3. Now, open channel is going to show up on the final, but not on exam 3. So this is within the internal flow category. Okay, and this is what we call open channel or partially filled conduits. And this is chapter 13. We spent time talking about completely filled conduits. That would be chapter 8. This is chapter 13. So we're just going to very brief overview of chapter 13. As I mentioned on Canvas, if you haven't watched that video, go watch there. Talk about, we're not going to have time to talk about compressible flow or pumps like I like to in a normal fluid semester. So picking the 3 topics, I picked open channel flow just to kind of move forward. Okay. So again, brief overview. The idea is this could be like a stream or a river or a drainage ditch, some kind of channel, some kind of conduit where part of the flow is exposed or open to the atmosphere. Or it could be, let's say I've got a duct or a conduit, a pipe, if you will, that is not completely full. So that means part of this liquid surface is exposed to the atmosphere. Right? So that means that the pressure anywhere that a surface or a fluid is exposed to the atmosphere, that means the pressure at that point is the atmosphere. And what that means is that we cannot apply back pressure. Gravity is the only driving force here. We cannot apply back pressure. What that means, well, I've got some fluid in an open channel here. And let's say that I wanted to apply a pressure to the fluid within here. So I get in there and I try to apply pressure, and you see what happens. It just dissipates, right? It doesn't go anywhere. I mean, so imagine I try to do something silly like that out in a lake or a river or stream, and I go stand out there in the middle of a stream to apply back pressure to the fluid. And so what do? I try to push the fluid downstream with my hands. And how well is that going to work? Right? That's just silly. I mean, that doesn't make any sense. That's open channel flow. You cannot apply back pressure in an open channel. All you can do is allow the fluid to flow downhill, or allow inertia of the fluid, the kinetic energy of the fluid upstream, to push over a small hump, small jump, if you will. Now, we're not going to have enough time to really talk about hydraulic jumps, but if you're thinking about going into civil engineering or spillway or floodway design, it's really, really interesting stuff to get into. Look through this chapter. There's a lot of information we are not going to touch on. We're going to try to get just the very basics, and but we're still going to be able to talk about quite a bit of interesting things. Okay. Again, because it's open and exposed to the atmosphere, the pressure everywhere is the atmospheric pressure, except until you get deep within the channel, and then you have rho GH above you, but that's it. So at the surface, the pressure is atmospheric pressure. If you can't apply more than that. So all we can do is allow, or the main thing we can control is gravity, a change in elevation. And here's the thing, if I'm moving water, I don't want that water to pick up a whole lot of speed. I don't want it to actually have a lot of kinetic energy. Water with a lot of kinetic energy is very destructive. It's very hard to control. It tends to erode or chew up whatever we flow it through, especially if it's picked up any gravel or anything like that, as most open channels do. So the more speed it has, the less time our designs will survive in a high-speed flow scenario. So a lot of times we want a very gradual change in elevation. The elevation is the only thing we can use to control the flow, and a lot of times we want it to be pretty slow depending on what we're trying to do. Now, if it's an emergency floodway and I've really got to move fluid out of the way very quickly, then maybe I do want a bigger elevation change. But it just depends on the scenario. But most of the time, I want that kinetic energy pretty low. Now, it's important that we understand, if I look at, say, the cross-section of a stream bed here, and if I look at it, it's really important that we understand that there's a difference between the average velocity and the velocity. And some of this comes in when we talked about the boundary layer last time. Right, there's a diagram in your text. It's probably going to be a lot better than what I'm going to draw here. Okay. If we went out, let's say I've got fluid flowing into the page here. Okay. It's important to understand that you're going to have different velocities within this fluid profile, right? The fastest is not going to be right here. The fastest is actually going to be right here. Okay, right in the middle of that channel is going to be your fastest speed. Now, let's say this is V1. Okay, V1 is going to be the fastest. Now, outside of that, then, you're going to have this area here, V2. It's going to be just a little bit slower. Right, so it's getting a little bit closer to the edge, a little closer to the wall. And then as you move, now right here at the surface, it's actually going to be a little bit slower, but it's still going to be faster than, say, the fluid right here along the very edge. That's going to be really, really slow. Right, this fluid down here. That's going to be your V3. That's your no slip at the wall, which is going to be almost zero. Right? V3 is going to be really small because the channel's not moving, so the fluid that's in contact with the channel wall, that's not going to move either. So at least it's going to try to stick to that surface. So again, the fastest flow is going to be right here in the center of the channel. It's going to slow down a little bit right here. Okay, the fluid that's in contact with this air, because the air is probably not moving at the same speed as the channel, assuming it's not a windy day. If it's not a windy day and the air up here is still, then that still air is going to try to slow down this layer of fluid right here on the very top. So right in the middle of this channel is going to be where you're going to have the fastest speed of flow. So it's important, again, it's important to understand the velocity at various points in a cross-section will vary, but we can use an average velocity for most design applications, meaning we just integrate all of the speeds at every little differential slice divided by the total area, and that will give us essentially an average across the area, and that'll be just fine. Okay, so we will use this average velocity or average speed for our design purposes. Now, there is this quantity here, SO or S naught. We call that the bottom slope. Okay. Now, I'm going to draw this with you. Okay. See if I can make some sense of it. So let's say I'm looking at the cross section of a stream bed here. Okay, and so let's say that I've got kind of a stream flowing through here. Okay. Now it would be pretty easy to take my tape measure and measure the length of this stream bed L. Okay. We could measure that pretty easily. Let's say we got a horizon here. Okay. And so we've got stream coming over the hill. And I don't know, maybe it goes into a waterfall. falls into a lake down here. Okay? I don't know. There's some kind of an open channel. Okay? So, as you guys know, I'm not an artist. Well, let's say I've got a length of open channel here. Okay? Now, that length is, so I'm looking now, so this is what this represents. It's just some stream bed. Now again, gravity is what's going to cause the fluid to flow from one end to the other. Okay? So fluid is flowing this way, and the reason we know that is because this is at a higher elevation than this one. Okay. Now, again, measuring this length, that's pretty easy. Just go take some kind of measuring device, go along the side of a stream bed and measure that length. It's a little harder to measure this elevation change right here, this change in elevation. That, without proper surveyor tools, that's a little more difficult quantity to obtain. But that's what we do need to know, that quantity, right? And describing that quantity, we can use what we call the bottom slope to describe that. Now, the bottom slope, and again, that's, if we look at this cross section of this stream, not looking down like this, looking from the side here, right? Delta Z. Again, this is the length that we can. The easy thing to measure is this length. Okay. Now, so this stream, two different drawings here. Again, this stream is at some angle down theta. So again, from this point to this point, it's a change in elevation. It's dropping. That's what causes it to flow. We can measure that angle theta, possibly. I don't know how easy that would be to measure. I don't do a lot of surveying. But let's say we can measure this angle here. Okay. Or maybe we want to describe that angle. Here's what we know. The tangent of this angle theta is equal to, right, I guess the cosine, isn't it? I apologize. I'm thinking here, yeah, cosine, no, sine. Here we go. I'm looking at my notes here, and I'm like, wait, that doesn't make sense. This makes sense. So, measuring x, the actual x distance, that would be difficult. Measuring L, that's pretty easy. But here's the thing, if delta Z and theta are pretty small, X and L are very close, right? This X quantity, the distance between the bottom here and then horizontally out to this point here, that's difficult to obtain if I'm right next to a stream bed. But this X is equal to L, the length of the stream, times the cosine of the angle that describes how quickly it drops. Now, if theta, right, if theta is approximately 0, if theta is very small, then notice that x is very close to L, because if theta is approximately 0, then the cosine of approximately 0 is approximately 1. This is x times L times 1. So we're saying is, as long as theta is really small, this x, which is really hard to go up next to a stream bed here and measure, we'd have to dig into the ground at an elevation right here and then try to put a tape measure across level. That's my timer. I'll have to pick up there on the next video.